This image is being created by a moving beam of light. The beam is tracing out a pretty familiar curve. It's a circle. But what happens if I change things a bit, like this? The new image looks like an ellipse. This image could be a parabola. And if I change things again, I get a two-part image. Couldn't this be a hyperbola? Well, we're going to explain exactly how those images were produced a bit later in the program. But we'll begin by concentrating on the images themselves. What we showed you certainly looked like an ellipse, a parabola, and a hyperbola. But were they? That's the question we're going to concentrate on in the program. And we'll end up by proving that what looked like an ellipse really was one. And on the way, we'll explain why these curves are collectively known as conics. Now, to prove that a certain curve is an ellipse, we have to show something quite precise. To be an ellipse, it isn't enough for a curve just to have roughly the right oval kind of shape. An ellipse is defined in a special way, as you know from the text. And we're going to have to show that our light image curve satisfies this definition. So let me begin by reminding you of the definition, in fact, of all three kinds of curve: the parabola, the ellipse, and the hyperbola. They're all rather similar in a way. In each case, we have a fixed point F, called the focus, and a fixed line, D, called the directrix. And the curve is the locus of a point P, which moves so that this distance, PF, divided by the perpendicular distance from P to D, is a constant. This constant, E, is known as the eccentricity. And what distinguishes between the different cases is the range of values that the eccentricity can take. When the eccentricity lies between 0 and 1, then you get an ellipse. If it's greater than 1, then you get a hyperbola. And when it's exactly equal to 1, you get a parabola. Now, let's look at one particular locus in detail. We'll take PF over PD to be a half, so the eccentricity will lie between 0 and 1, and we're going to get an ellipse. We'll choose the focus, F, to be at x equals 2 on the x-axis, and we'll use as directrix the line x equals 8. The point at x equals 4 on the x-axis is on the locus because this length is half this length. Similarly, the point P is on the locus because this distance PF is half of this distance PD. We've marked in the midpoint of PD to make that clear. And all these points are on the locus. This point at x equals minus 4 on the x-axis is also on the locus because this length, which is 6, is half of this length. If we carry on, the curve closes up to give the whole ellipse. Now let's generate another ellipse, and let's concentrate on what happens when we change the eccentricity. We'll draw the ellipse with eccentricity a quarter, and we'll draw it so that it cuts the x-axis at the same points as this one. Of course, doing this will mean the new ellipse will have a different focus and directrix. But it's the shape of the ellipse we'll be interested in, so let's not worry about their precise locations. Let's draw it out. This ellipse with smaller eccentricity is less squashed than the previous one. Now let's look at an ellipse which has larger eccentricity than the first one. We'll take E to be 2/3. This one is more squashed than the first one. Now let's see what happens as we continuously change the eccentricity. As E increases, the ellipse gets flatter. Then as we decrease e, the ellipse becomes more circular.
So that shows how the eccentricity changes the shape. But there's another thing that we can see from this ellipse. Because the ellipse is symmetric, then this point, f dashed, and this line, d dashed, form another focus directrix pair, which also generate the ellipse. But we must remember that this focus goes with this directrix, and this focus goes with this directrix. Because this property applies to all ellipses, we say that the ellipse has two foci and two directrices. Now let's investigate the hyperbola in the same way that we looked at the ellipse. We'll begin by drawing out the locus of a point. And then we'll see what happens as we vary the eccentricity. This time, I'm going to choose the focus at x equals 2 on the x-axis, and the directrix to be the line x equals a half. We'll find the locus with eccentricity 2, that is, which satisfies pf over pd equals 2. Well, one point on the locus is at x equals 1 on the x-axis. These points are also on the locus. But wait a minute, have we really finished? There's actually another point on the x-axis which satisfies pf over pd equals 2. Look at the point x equals minus 1. Pf is this length, that's 3. And pd is this, 1.5. So pf is twice pd, and so x equals minus 1 is on the locus. And so there'll be another part of the curve passing through this point. So there's our hyperbola with eccentricity 2. Now we'll draw another hyperbola with larger eccentricity, but which passes through the same points on the x-axis. We'll take e equals 4. Of course, we'll need a new focus and a new directrix. And here's the locus corresponding to this larger eccentricity. Now let's do one with smaller eccentricity, say root 2. And again, let's see what happens as we continuously change the eccentricity. So, as the eccentricity gets larger, the hyperbola gets wider. And as it approaches 1, the hyperbola becomes more narrow and squeezed about the x-axis.
Just like the ellipse, the hyperbola also has a second focus and a second directrix because of the symmetry of the curve. Well, we've seen how ellipses and hyperbolas are defined and what shapes they have for different eccentricities. Let's go back now to those images which we showed you at the beginning of the program. Remember, one of our aims in this program was to show you that what looked like an ellipse really was an ellipse. We've reminded you of the definition. Our next step is to show you exactly how those images were produced. Well, this is where the business about the curves being called conics, or conic sections, comes in, because we actually generated those curves from cones of light. The light was generated by a laser. By means of a rotating mirror, we focused the beam to make a cone. Then by putting an opaque screen into this cone of light, we could actually see the path traced out by the laser beam. So the image was actually a section of a cone.
So let's look in more detail at what happens when you slice a cone with a plane. I've got some solid models to help us do this. This model is only part of a cone. The other part you could imagine up here. But in fact we don't need it now because this plane only intersects this part of the cone. So the curve of intersection round here is all in one closed piece. Let's take the top off and see the curve of intersection. The shape appears to be an ellipse, but what if I take cuts at different angles through the cone? Am I always going to get shapes which appear to be ellipses? Well, let's look at things systematically and begin with the simplest situation. Here I've rearranged things slightly. This cone is complete and I've got it on its side. Of course, you have to imagine that both halves extend indefinitely. To begin with, we've put the plane through the cone perpendicular to its axis of symmetry. And, because of the shape of the cone, you'll know immediately the shape of the intersection. It's a circle. Now let's see what happens as we change the angle of this intersecting plane. In the top half of your picture is the cone with the intersecting plane passing through it. And in the bottom half is the shape that is cut out by the intersecting plane. In this position, the plane is nearly vertical, and so the shape, though elliptical, is almost circular. But as the plane moves further away from the vertical, so the shape becomes longer, and it still looks as if it's an ellipse. Eventually, we lose one end of the shape off the screen. Of course, the cone really continues indefinitely on either side of the screen. The plane is still cutting just one half of the cone, and so the shape is still in one piece. It's still an ellipse. But now, if we continue to turn the plane, the whole situation changes radically. The plane now intersects the left part of the cone as well as the right part, and the curve is no longer in one piece. The intersection can no longer be an ellipse. The intersection curve has two parts, like a hyperbola.
Well, let's take a closer look at what we've got. Here's the intersecting plane through the cone. This time it intersects both halves of the cone. Now I'll remove these two sections, and then we can see the shape of the intersection. The separate intersections of the plane of the two parts of the cone give these two parts of the curve, extending indefinitely. That's just like a hyperbola. We saw that we got an elliptical shape, on the other hand, when the angle of the plane was such that it cut just one half of the cone in a closed curve. But wait a minute. What about parabolas? Where do they fit into the story? Is there a position of the plane which neither cuts both halves of the cone, nor cuts just one half of the cone in a closed curve? Well, think about that. And to help you, let's look at part of that last animation again and see if you can spot at which point a parabolic curve appears. Here it's an ellipse. The plane cuts only one half of the cone. And here it's a hyperbola. It cuts both halves. But what about here, where the plane is parallel to an edge of the cone? It certainly only cuts one half, but the curve of intersection extends indefinitely to the right. So there's one special angle of the plane where it's parallel to an edge of the cone. When it's in that position, it cuts just one half of the cone in this curve, which never closes up. So that's where the parabolic curve appears. So intersecting a cone with a plane at varying angles produces these familiar-looking shapes. But what we haven't done is prove that each of these curves really is a parabola, a hyperbola, or an ellipse, as the case may be. And that's what we're going to do now for the case of the ellipse. We'll have to use the definition of an ellipse, and we'll have to apply it in this situation. Now, what distinguishes this configuration from the others? It's that the angle of inclination of the plane, the angle alpha, is smaller than the base angle of the cone. That's beta. In fact, these two angles, which are fixed for a given configuration of the plane and the cone, play an important part in the proof, as you'll see. In order to use the definition, we'll need to show that each point on the curve satisfies the focus directrix property. But where's the focus? And where's the directrix?
Now there's actually a delightfully simple way of finding them, but you'd never be expected to think of it for yourself. What we do is to fit a sphere inside the cone, like this one, so that it just touches the inclined plane in this point, F, and also just touches the cone in this horizontal circle. From the choice of this label, you've probably guessed correctly that F will turn out to be the focus. But what about the directrix? Well, this horizontal plane through the circle intersects the inclined plane in this line, and this will turn out to be the directrix. Notice that any line in this inclined plane passing through F is a tangent to the sphere at the point F. Also, any straight line in the surface of the cone is a tangent to the sphere at the point where it intersects this circle. Now, to show that this really is the focus and this line is the directrix, and at the same time to show that the curve is an ellipse, what we need to do is this. Take an arbitrary point P on the curve, join it to F, and draw PD perpendicular to this directrix line. We'll calculate the ratio PF over PD and show that its value is independent of the choice of the point P. In fact, we'll show that the ratio depends only on the angle of inclination of the plane and of the angle of the cone. These were the angles alpha and beta that we saw previously. Look at the point P. In addition to the lines PF and PD, we've drawn PL. That's a line on the surface of the cone from P to this horizontal circle. So, PF and PL are both tangents to the sphere. And as you saw in the pre-programmed work, this means that they're equal in length. That's the beautiful part of the construction, because it enables us to look at the equivalent ratio, PL over PD, which is easier to calculate than PF over PD. So let me explain how to do that calculation. We drop a perpendicular from P to this horizontal plane to obtain these two right-angled triangles. This angle is the angle of inclination of the plane, and this angle is just the angle of the cone. These triangles contain PL and PD, and they also have PM in common, and we can use this to find the ratio PL over PD that we want. We do it like this. Sine alpha is opposite over hypotenuse. That's PM over PD. And similarly, sine beta is PM over PL. Now dividing these gives sine alpha over sine beta, which is PM over PD divided by PM over PL. and that's PL over PD. So we've evaluated PL over PD, and our result, sine alpha over sine beta, is totally independent of the position of P. So PF over PD, which is the same as PL over PD, is constant. This shows the curve must be a conic. And what's more, we now know its eccentricity is sine alpha over sine beta. But alpha is less than beta, so the eccentricity is less than 1, and therefore we have an ellipse. And that completes our proof. Actually, we could use a similar method to prove the results for the other conics.
What we've really done in this program is prove the equivalence of two different ways of defining an ellipse. On the one hand, the way that you saw in the unit, and at the beginning of the program, by the focus directrix property. And on the other hand, the definition of an ellipse as the curve of intersection of a plane with a cone in a certain kind of configuration. Now, each of these definitions has its own particular advantage and beauty, and perhaps also its own disadvantage. I think that the cone definition is perhaps geometrically the more satisfying. Certainly it's the older definition. It's the one the Greeks used in their definition of conics. Also from this definition, it's easy to visualize how one curve can be transformed from an ellipse to a parabola to a hyperbola. And it also solves a little problem about the family of conics, which you may have noticed. And that is that, as you saw from the earlier animation, when you decrease the eccentricity of an ellipse, you get a curve which is more and more nearly a circle. And yet, strangely enough, you can't define a circle by means of the focus directrix property. But in terms of the cone, you can easily see what's happening. Because what we're doing is making the plane of intersection of the cone more and more nearly perpendicular to the axis of symmetry. And from the point of view of the cone, the circle is therefore a perfectly good conic. On the other hand, it's true to say that it's rather difficult to write down the equation of a conic starting with the cone definition. The focus directrix and the cone definitions aren't necessarily the only definitions we could use. If we go back to thinking about the focus directrix property, it actually does suggest other kinds of definition which may lead to the same curves, or could possibly lead to other interesting curves. And that's the idea we want to leave you with. The possibility of defining curves as loci by properties similar to the focus directrix property. For example, suppose we had to find a locus defined like this. Here f and f primed are two fixed points, and we're looking at the locus of points P, which satisfy PF plus PF primed as a constant. You may have come across this before. On the other hand, we could look at the absolute value of the difference of PF and PF primed. Well, to examine loci that you get like this, there's a little problem that we've set for you to do after the program.